All right, continuing on here, we're looking at our pre-calculus exam review. The focus of this section is characteristics of functions. To find all the exam review lessons, please take a look at our playlist under exam review or the playlist under pre-calculus. So for this one here, we're taking a look at characteristics of functions. We start off, if we look here, we are starting off with the difference between a relation and a function. So we're given three different relations here. Recall the definition of a function is such that for every x in the domain of f, there exists a unique y such that f at x equals y. So essentially what that means is for every input value, you see like for this relation given to us here, every input value, so that's 0, 2, 9, 7, and 12, each of those input values goes to exactly one unique output value. So you're not going to two different places for a given input, two or more different places. So if you take a look at our first relation here, we are seeing that 0 is being sent to 1, 2 is being sent to 6, 9 is being sent to 4, 7 is being sent to 2, and 12 is being sent to 3. So each of these values is going to a unique output value, unique y value. So this is in fact a function. This relation is a function. Let's take a look at our next example. In the next example, we don't have that. If you take a look here, 0 is being sent to 4, but then 0 is also being sent to 6, and 0 is being sent to 8. So this relation is not a function in this example here. So in example 2 here that we see, this is a relation that is not a function. And lastly, taking a look at this example here, sometimes it is easier to express it in mapping form. So in this case here, -7 is being sent to 0, 4 is being sent to 2, 4 is also being sent to 1, and right away we don't even have to continue. I already know that this is not a function because of this sequence here. We have 4 being sent to 2 and 4 being sent to 1. We can see here that in the third example, this is a relation, but it is not a function. Let's continue on our exam review. Now we're going to be looking at the idea of function notation. So in this question here, we're given the following function, and they want us to evaluate p at -6, p at 0, p at 3, function at z squared, and the function at 4 minus x. So taking a look at here, the idea with function notation is everywhere you see an x, if we're looking at part A, we're going to change that to a -6, giving us. And you'll see here in part A, everywhere I saw an x, I changed that to a -6. So we put these values here. Evaluating this, -2 and -6, give me that +12. Watch out with the double minus sign here. This -6 squared is going to be +36, but you do have that minus sign from before to recopy back down. Simplifying, I end up getting p at -6 is -21. Let's go ahead and try b. For part b here, you'll notice we're valuing the function at 0. Essentially, what's going to happen is everywhere you see an x, you change that to 0, and your answer will just become a 3 here. And as you can see here, the -2 and the -x squared all cancel off because of that 0. Looking at C, we're now going to evaluate this at 3, giving us. And evaluating P at 3, everywhere I see an X, I change that to a 3 here. And you'll notice here I do my calculations. This becomes -6. Again, common mistake here. This output is going to be a -9, as you see. The reason for that is that power of 2 is being applied just to the 3. That minus sign is out in front and being applied afterwards. So our final answer for C is going to be -12. Continuing on here, if you look at part D, we're valuing the function at z squared. So p at z squared is going to be everywhere I see an x, I'm changing that to a z squared. Everywhere I see an x, I change that to a z squared. So this last expression will be z squared to the power of 2. And lastly, simplifying this up here, we get 3 minus 2z squared minus z to the power of 4. And wrapping this up here, evaluate the function at 4 minus x. So everywhere we see an x, we're going to be changing that to a 4 minus x. And evaluating this, we end up getting -x squared plus 10x minus 21. All right, let's take a look at another example. Continuing on here, we want to practice function notation with a piecewise function. So again, we have a piecewise function. This is a collection of a linear function, a quadratic function, another linear function kind of broken up at, as you can see, 7 and 11 here. We want to go ahead and evaluate this function. So take a look here at A. They want us to find the function at 2. So the function at 2 2 would satisfy this condition. 2 is less than or equal to 7, so we're within this interval here. We take on our linear function. That'll be 1/2 times 2, which is 1. For part B, we want to evaluate the function at 7. So again, where does 7 occur? 7 occurs at this interval once again. This will be 1/2 times 7 becomes 7 over 2. For part C, we want to evaluate the function at 8. This is going to be g at 8. G at 8 falls within this interval here. So this is going to be 8 squared plus 1, which is 64 plus 1, which is 65 here. Taking a look at D, they want us to evaluate the function at 11. Well, 11 satisfies this interval here, in which case we take on our linear relationship of 3 minus x. This becomes 3 minus 11, which gives us -8. And lastly, for part E, they want us to evaluate the function at 14. G at 14 is again within that 3 minus x. This will be 3 minus 14, and giving us -11. Let's take a look at another example here. So for the next example here, they want us to use our function notation, and what we're going to do is calculate f at x plus h minus f at x over h. In calculus, you guys will study this as the slope of your secant lines. This is your process of calculating the derivative of a function at a given point x. So this is good practice for that, and good practice using your function notation. So they want us to find the following expression and simplify it. So in this case here, I want to find out, I already have what f at x is. They want us to evaluate f at x plus h. Well, f at x plus h is going to be everywhere I see an x. I change that to an x plus h. And then they want us to put that into this equation here. So subbing that into this equation, we get, and you'll see here I went ahead and factored the 3 out of the numerator. And if you notice here, you have a difference of squares set up here. I can go ahead and factor this as a difference of squares, which will give us, again, treating this as your x and this as your y, and getting x minus y times x plus y. You can see right away the x's cancel. I'm just left with an h. This ends up simplifying to become, and you'll notice the h's cancel, and we end up getting here 3 times 2x plus h. And as a reminder here, I was allowed to cancel off these h's because we were initially dividing by h in the original question, so we're implicitly assuming that h is non-zero. So because of that, I was allowed to cancel off these h's below here, and our simplified expression is 3 times 2x plus h. Let's take a look at another one of these questions. So for this question here, same idea. We want to calculate the slope of that secant line. So to remind you, it was f at x plus h minus f at x over h. And let's sub all that in. Subbing this in, we get, and we want to be able to simplify this expression. First step is to go ahead and get a common denominator in the numerator, giving us, and continuing this on here, I end up getting 2x minus 2 times x plus h over x times x plus h. So I got myself a common denominator here. Let's go ahead and simplify this up a bit. You'll notice here I can distribute that 2. We get a little bit of cancellation. Simplifying gives us, and you'll see here the 2x's cancel. I end up getting -2h over x times x plus h. The whole thing is divided by h. I want to go ahead and multiply it by the flip. So keep in mind this is a fraction on the bottom, a fraction on the top. So we can change that division operation to multiplication and multiply that by 1 over h. Again, we're assuming here the h is non-zero. That's implicit in that slope of the secant equation. We know h is non-zero, so these h's will cancel. And our final answer is -2 over x times x plus h. And this becomes our simplified expression for the slope of the secant lines here, f at x plus h minus f at x over h, when you are looking at the function 2 over x, your reciprocal function. All right, let's take a look at our next example. The next example here, we're now moving on to the idea of domain of functions. Recall the definition of the domain of your function is the collection of all x values such that f at x exists. So in this case here, we want to find out for what values of x is the following function h at w defined. And those values where that function is defined becomes your domain. So in this case here, our first step is to fully factor this to see where you get any sort of issues. One issue would be when is the bottom 0. So let's just fully factor the top factors quite easily as w plus 2 times w plus 1, and the bottom will factor as w plus 6 quantity squared. So right away we see that if w equals -6, the function is undefined. Any other location here is completely fine. Notice here that h at -2 and h at -1 are both equal to 0, and those are defined values, and that does not go outside of the domain of your function. However, if I evaluate this at -6, we end up getting here some number in the top and dividing by 0 in the bottom. and that's undefined. And because of that, you have to take that out of your domain. So the domain of this function here, h, is going to be the collection of all real numbers such that x is not equal to -6, and that's the only element that has to be taken out. Moving along here, we want to find the domain of h, our function here h, and this is the square root of 8z squared minus z minus 20. So first question becomes, when is the quadratic that we have underneath the square root, when is that less than 0? Because you can't take the root of a negative number and have that part be part of your domain of your function. So in this case here, I want to find out for what values of z is z squared minus z minus 20, when is that below the x-axis? So quickly we can see here that z squared minus z minus 20 will factor into z minus 5 times z plus 4. So I know visually that this is a quadratic that has roots at -4 and 5, and I know that it opens up. And I can tell that for this quadratic, the values between here and here, so in this case here, between -4 and 5, we can see that that quadratic is below the x-axis, in which case we'd be taking the root of a negative number. So the domain that I'm interested in, let's highlight this in green, is I want everything at 5 or greater, or at -4 or less. So in this case here, the domain of h is going to go from -infinity to -4. I'm going to put a square bracket on that because at -4, your quadratic is 0, and the square root of 0 is fine. Or I'm going to take a value, square bracket, at 5 all the way up to +infinity. And we have our domain of the following function. Let's continue our review. So now we're getting into the idea of sketching our piecewise functions. For this question here, let's draw our Cartesian plane and identify sort of, these are the breaking points. 3 and -2 are where your piecewise function is changing. It's changing, in this case, from a quadratic to a linear flat line, then a linear to another linear at sort of a slant. So let's take a look and kind of partition that up on our Cartesian plane. So breaking this up on our Cartesian plane, we have x is less than or equal to -2. Then we have -2 to 3 and 3 to infinity. So let's go ahead and note some of these values here. Let's go x is greater than 3. When x is greater than 3, we have ourselves a quadratic. So what we can do here is right at 3, we want to see whether these two values, in this case, do the quadratic and the line y equals 4, do they line up? Well, we see the function at 3, by definition, is equal to 4. So we can see here, as I approach 3 from the right-hand side, and I'm getting closer and closer to 3, but still to the right of 3, we're taking on the quadratic equation. So what happens is this ends up approaching 3 squared, which approaches 9. So I'm going to put an open bracket on this. And once we're at 3, the function will drop down from 9 all the way to, let's say, 4. Let's make 4 here. And it drops down to 4. And we have that value consistently all the way across until we hit -2. And then right at -2, it's changed to our linear. Now, to the right of this, 3 is a quadratic, so this will continue on here. The quadratic is such that the vertex is at 0, so it's really going up like this. So we want to kind of keep that motion going of the quadratic. If you want, you can kind of even sketch the dotted line and then continue that dotted line. So this will continue on as our quadratic in this area. I can kind of erase this now. You don't want to draw it like this. That'll make it look like your vertex is actually happening at 3, 9, which it's not. It's happening at 0, 0. Right at 3, it drops down to a horizontal line. Continue that on. Right at -2, again, we want to see whether these line up. So you'll notice here that the function at -2 is equal to 4. So we actually have a solid dot here. And then right as we go to -2 from the left-hand side, it takes on this linear. If I sub in -2 for this x value, I end up getting 3. So they don't line up again. Ends up being a linear at 3. So we're going to put an open bracket here at +3, say right about there. And that'll continue on decreasing. And because the line y equals -x is decreasing as I read it from left to right, the graph will look something like this. As we continue on in this direction here, it'll continue on in this fashion. And the idea here is that the y-intercept is about 1, so somewhere along that line it'll cross, and that'll represent our 1. So this is a sketch of our piecewise function f at x here. Let's take a look at another example. So in the next example here, we want to sketch the following piecewise function. This one's a little bit easier. There's only one breaking point that is happening right at 1. So at 1 here, again, we want to know, do these two piecewise functions, these two quadratics, did these two quadratics line up? So again, evaluate the function at 1. Evaluating the function at 1, we see we take on the x minus 2 quantity squared function, in which case this will be 1 minus 2 squared, which is 1. So the function right at 1 is 1, and we can put a solid dot there right at 1. We'll let this represent 1. And now the function as we approach 1 from the right-hand side, as I'm approaching 1 from the right-hand side, we get 2 minus 1 squared is 1 as well. So this time they actually do line up exactly. And what we have here are two different quadratics. To the right of 1, we have a quadratic that has a vertex at 2, 0, which is located roughly here, is our vertex for our quadratic x minus 2 quantity squared. And so what's going to happen here is the quadratic will go down, hit my vertex of 2, 0, then go back up. And then to the left of 1, we take on a quadratic that opens downwards and has a vertex at 0, 2. So now the vertex is up here at 0, 2. And that quadratic will now look as follows. And this is a graph of our piecewise function f at x here. This value right here, they don't ask it, but that value is going to be where this crosses the x-axis. That's going to be at negative root 2. This quadratic, if we would have continued this, if it would have continued being the 2 minus x quadratic, this would have continued on and crossed maybe right around here at that sort of positive root 2 value. But again, right at 1, it switches and becomes the x minus 2 quadratic, so it opens upwards and has this flow to it, and that vertex ends up happening right at 2, 0. All right, let's take a look at some more examples of function notation with multiple functions. So for the following problem here, we're given a function here h at w defined as this following quadratic, then a function f at w defined to be another quadratic, and they asked us to go through some operations here. So part A, they want you to evaluate h minus f acting on w. By definition, h minus f is its own function. When that acts on w by definition, that was h at w minus f at w, which is going to equal w squared minus 4w minus 2 plus w squared. Again, don't forget to put brackets around that f at w to distribute that minus sign into both the 2 and the w squared. This ends up becoming negative 4w minus 2. After simplifying, the w squareds cancel, and we are done. Let's take a look at b. So for b, it's f plus h acting on negative 4 this time. Again, by definition, that's f at negative 4 plus h at negative 4. This gives us, and you'll see here, the only mistakes that can be made here is don't forget when you're substituting something in, you put brackets on that entire expression. So in this case here, it's negative 4 to the power of 2, negative 4 to the power of 2 for these values here. All right, let's take a look at c. For c here, they want us to evaluate f at h, but again, you'll notice here they don't tell you what the function is acting on, so they actually want you just to create the function f times h, which will be 2 plus w squared times w squared minus 4w. Expand this out, we get 2w squared minus 8w plus w to the power of 4 minus 4w cubed. Simplifying this, we get. Now you notice here there's nothing to simplify, but we can arrange this by descending order by the powers here. So this will be w to the 4th minus 4w cubed plus 2w squared minus 8w. All right, taking a look at d here, they want us to evaluate h over f acting on w. And you notice by definition, this is h at w over f at w, which is exactly equal to w squared minus 4w divided by 2 plus w squared, and that becomes our new function here. So you notice the difference between these two here. This is f times h, and they didn't really give a variable that we're multiplying by, and this is h over f acting on w. So this is to be expressed as a function of w. This one here, I chose to write it as a function of w, but based on the definition, I could have written this with any variable as well. So when someone just writes this, they're not really indicating what variable you're referencing. So I could have changed these to x's, which would have been probably the standard form. I could have written this as x to the 4th minus 4x cubed plus 2x squared minus 8x. But this is not wrong either. I chose a variable of w. And here they explicitly told you create a function with input value as a w variable. All right, let's take a look at some more questions. So one final question working on our function notation here. They give us two functions here. Function A is 2w squared plus 9, and function R is 1 minus 2w minus w squared, and they want us to compute the following here. So you'll notice here we're not computing any values here. They're just creating new functions. So let's go ahead and do that. For part A, it's multiplication. So we're going to go ahead and take the function AR acting on W. By definition, that's A acting on W times the function R acting on W, which will equal 2w squared plus 9 times 1 minus 2w minus w squared. All right, take a look at B here. We want to calculate A composite R acting on W. By definition, this is going to be A acting on R acting on W. And R at W is 1 minus 2w minus w squared. And now what I'm going to do is everywhere that I see a w in my function A, I'm going to be changing that to a 1 minus 2w minus w squared. So this gives us 2 times 1 minus 2w minus w squared, all to the power of 2 plus 9. Expanding and simplifying, we get, and we end up getting here 2w to the fourth plus 8w cubed plus 4w squared minus 8w plus 11. And again, I had to expand out this product of this two trinomials here. So I had to go ahead and do FOIL on this, each term 3 times, and it ended up giving me this long expression. I went ahead and just collected up like terms, simplified everything up, distributed, and one final simplification, and we have our fourth degree polynomial that this is equivalent to. Let's take a look at C. So for C here, we want to take R composite A acting on W, which is R acting on A at W. And by definition, A at W is going to be 2w squared plus 9. And now for my function R, which is right here, everywhere I see a w, I'll be changing that to a 2w squared plus 9. Expanding and simplifying, we get the following. And expanding and simplifying this out, I get negative 4w to the power of 4 minus 40w squared minus 98. Keep in mind here, this was to the power of 2. You have to actually expand this out, square the first times second times 2, square the last, and then I distributed that minus sign into the brackets afterwards. Simplifying, we get the following. Let's now take a look at D. For part D here, they want us to calculate A composite A acting on W. So this is going to be A acting on A at W. And in this case here, our A at W is 2w squared plus 9. And now again, everywhere I see an W, I'm going to be changing that in my function A to a 2w squared plus 9. So this is going to give us 2 times 2w squared plus 9, and then plus 9. And don't forget to put that power of 2 on the top as well. So expanding and simplifying, we get the following. We end up getting 8w to the fourth plus 72w squared plus 171. All right, that concludes this lesson on Precalculus exam review. The focus again was function notation, working with functions. Take a look at the end of this lesson. Some of the videos are linked at the end. You can check out those or go directly to the playlist under exam review or the Precalculus section, and you can find a complete exam review for Precalculus. Thank you.